Okay, good morning. This is Projectile Motion 2. So after we discuss Projectile Motion 1, we proceed to Projectile Motion 2. So to recall, free fall is a one-dimensional motion where the object only moves either upward or downward. And Projectile Motion 1 is a two-dimensional motion wherein the object is moving simultaneously horizontally and vertically. So where the horizontal motion is at constant velocity and the vertical motion is accelerating due to gravity at 9.8 meters per second squared. So the difference between projectile motion 1 and projectile motion 2 is that the object in projectile motion 2 is thrown or projected at an angle. So unlike projectile motion 1, it is only thrown or projected horizontally. So this time there is involvement of an angle as it is thrown. So the angle is somewhere right here. So this angle right here is the angle of projection. And then if you observe, there is initial velocity that is colored red arrow, and then the initial velocity here is not equal to the initial velocity in the x, and also is not equal to the initial velocity in the y, but this initial velocity in the x and the y is the component of your initial velocity. So if we want to determine the initial velocity, so it is a combination of initial velocity in the x and initial velocity in the y. So as the object moves upward, you would observe that initial velocity in the x, or the velocity in the x, is not changing, whereas this one right here, the y component of your initial velocity, as it moves upward, decreases until it becomes 0, and then as it moves downward, it then increases. Again, the initial velocity in the x is still constant. So as the object moves upward, its initial velocity in the y, or its velocity in the y, decreases until it stops right there, or its velocity in the y is 0, and then as it moves downward, its velocity in the y increases by 9.8 meters per second squared. So the characteristics of a projectile motion 2 is that the same as with projectile motion 1, the horizontal motion has a constant velocity, and then the vertical upward motion is decelerating, meaning to say the velocity decreases. This y component here of the velocity decreases by 9.8 meters per second for every second until it reaches the highest point wherein the vertical velocity is 0, and then when it starts to move downward, the vertical velocity increases by 9.8 meters per second squared. So in terms of equation, so we'll use the same equation as with projectile motion 1 in terms of horizontal motion. That is, velocity in the x is equal to the distance in the x divided by the time. And then for the vertical motion, we still use the same kinematic equation for the vertical motion. What is added in the scene is that we now have this equations, which is just a part of our when we discussed vectors. So if you recall, this formula right here is just Pythagorean theorem, which says that the hypotenuse is equal, the square of the hypotenuse is equal to the square, or the sum of the square of the two sides. And then this one just comes from the trigonometric functions, or the SOHCAHTOA. So you can use this formula to determine the initial velocity and the y, and you can also use this formula or equation to compute for the initial velocity in the x, given the initial velocities and the angle, of course. So let's do some practice problems. Suppose a golf ball is hit off the tee with an initial velocity of 30 meters per second at an angle 35 degrees to the horizontal. What is the horizontal velocity and what is the initial vertical velocity? So the initial velocity is this vector right here, and it is projected at 35 degrees from the horizontal or from the ground. And this vector right here has an x component, we call that one vx, and a y component, we call that one the vy. And since we are given with the initial velocity, we can use this formula right here to compute for the initial velocity in the x, or vx, and the initial velocity in the y, or the viy. So to proceed, now we are only given with initial velocity and angle. So this one is given, the initial velocity, and the angle is also given. So we can compute for the initial velocity in the y and the initial velocity in the x. So to compute for the initial velocity in the x, vx, that is cosine theta times vi. Substituting values, we have cosine 35 degrees times 30 meters per second squared, the initial velocity. So our initial velocity in the x now is 24 meters per second. And then for the initial velocity in the y, formula is this one, sine theta times vi. And substituting values, we have sine 35 degrees times 30 meters per second. And the initial velocity in the y is 17.21 meters per second. Now this would tell you that as the object moves sideways or horizontally at 24.57 meters per second, it is also moving upward at 17 meters per second. And the resultant for this vector is this vector right here, which is just equal to the initial velocity of 30 meters per second. Okay, next, let us, or we are asked on how much time it took for the golf ball to reach the highest vertical position. So as the ball moves upward, it somehow reaches a highest vertical position. Question is, or we are now asked of how long will it take, or how much time does it need to reach that highest position. So we have here equations for time, and we have two equations for time. And then equation 1, g is given, initial velocity in the y, and the final velocity in the y is given, so might as well we use this equation right here. For equation 2, we are not given with a dy. So we are not given with dy yet, so let us just use equation number 1. Okay, so this is the equation for, or the solution for the time, so the t up. So this equation is rearranged putting t to the left side of the equation. So substituting values now, so the velocity final as the ball reaches the highest position, the velocity is 0. And then viy, we already have this one as this equation right here, sine theta times vi, or sine 35 times 30 meters per second, divided by the value of gravity. So we have 1.775 as our value for time. So the ball reaches at the highest position in 1.7 or 1.8, approximately 1.8 seconds. So again, this equation right here is this one right here. So next, how far horizontally will the ball reach? So we are now asked with the range or the x max, or how far will the ball reach horizontally from this starting point to that side right there. So how far will the ball reach? So we are now asked with dx. So we only have one equation or formula for dx, and that is rearranging that one, we will have dx equals to bx times time. We can compute for bx using this formula, and which is just found here in our equations on the left. And for time, we are not given with time, so we will have to compute for time using this formula right here. Although we have computed already time, but if we did not know time yet, we can just compute the value of time using this equation right here. Now, since we are asked of the total time, so we need to multiply it by 2, because the time that you have computed using this formula a while ago is only up to t up. So t down is just the same or equal to t up. So we might as well multiply t up by 2, and that is now the total time for the golf ball to reach the other side, or before it touches the ground, after it was hit. So substituting values now. So again, to recall, VIY here is this equation because this one is just 0. So substituting values, we now have this equation: cosine 35 times 30, which is our VI, times 2 times 0 minus sine 35 times 30 divided by 9.8. Now, if you look at this equation, we would expect that our answer is negative. Now, if the object is moving upward, the object is slowing down, the acceleration for that one is negative 9.8 meters per second squared. So, if you do not put negative here, then you will have an answer that is negative. So, you must remember that if the object is decreasing its velocity, the acceleration is negative. So, our answer now for dx is 86.3 meters, or this one right here is around 86.3 meters. Okay, so another practice problem. A cannonball is fired so that it shoots to a container at an unknown distance. So the unknown distance is this one right here. So we do not know how long this distance is. You can also have it by saying that where are you going to put this container so that the cannonball shoots into the container. So we are asked of the distance from the cannonball, or distance of the container from the cannonball. So we are again computing for dx because that is the horizontal distance. So the formula is dx is equals to velocity times time. Now vx is again this formula right here, the initial velocity in dx, or vix is just the same as vx because the velocity is constant horizontally. And then the time, we can also use this formula right here for time. However, the time you will get from here is only from the starting point towards the highest point. So you need to multiply your answer for time when you are using this one. So this should be multiplied by 2, so that you are actually getting the time it took for the cannonball to reach the first half and the second half of its travel. So we now have a formula. So this one is bx, and multiply time. This whole equation here is the equation for time, so multiply it by 2. so that we are considering the upward and the downward motion also. Then substituting values, we now have our dx to be 63 meters. Next, so okay, just disregard this one. So the correct answer is 63 meters. Letter B, what is the maximum height dy of the cannonball? So how far, or how far vertically, or what is the highest point that the cannonball will reach? So that is referring to this point right here. So since we are considering this one as a level surface, so our dy should start from this position here to that highest position. So that is what we are computing. So to compute for dy, we are given with the initial velocities and the angle. So we can use this. We are not given with time, so we can use this formula. So we know that this one is 0. Final velocity as the ball reaches the highest position is 0. So we are left with this equation right here. So rearranging that one, we have dy is equals to df squared minus viy. And then to recall, viy is this equation right here, which is this one right here. Then we have the square, so we do not forget the square. And then that is 2 times gravity. Substituting values now, we have 13.17 meters, or approximately 13 meters. So this height right here is approximately 13 meters. Next, the total time of flights of the cannonball. So we are asked of how long will it take for the cannonball to reach the container after it was released. So that is T up plus T down, or the total time, or you can also just multiply T up by 2. So we can use this formula to compute for the T up, or twice T up. Okay, this is now our formula. So arranging, we now have BF velocity final in the y minus velocity initial y over g. And we know that VIY again is this formula right here. So that is this one right here. And then substituting values, we have 0 minus sine 40 degrees times 25 divided by 9.8. So the answer is 3.28 seconds. So we have here, still have to multiply this one by 2, and the answer is 3.28 seconds, or 3 seconds, 3.3 seconds. Okay, the last one is, if the container, compute for dx, we are to compute for dx, this one right here, up to that position there. If the container is not present, so the container is not present, and we know that this one is level with here, and we know that this one right here is, our dy right here is 60 meters, and we know, or we have computed our dy here, which is also around 13 meters, approximately 13 meters. You can still recall with the previous our previous answer. So we are to compute dx. So again, the formula for dx is here. So that is, so the time here is again t up plus t down. Now take note that t up is not the same as t down, because it already took longer for the ball to reach this position right here. So the T up that is, or the T down that is equal to T up, is only up to this position. So since it's already past this position, So we would expect to have higher T down compared to T up. Okay, let's substitute. Let's now continue. So we have this one as our equation for Bx, and our T up is this one coming from this equation, and then this one right here coming from this equation right here, wherein we considered dy and gravity. So the initial velocity, as this one moves from the highest position downward, initial velocity is 0. So we are left with this one, and then rearranging that one, we have square root of 2 dy over g. So let us now check. Substituting values, we have this equation. So cosine 40 times 25, and then this is velocity final is 0. This is VIY, then gravity, then this is 2 times dy. So dy is 13.17 plus 60. So that comes from here 60 plus the 13.17, our answers a while ago. So we added that one because that is the whole dy, and then divided by 9.8. So this one right here is Vx, the value of computed value of dx. This one is for T up, and then this one is for the T down. So you would expect that T down is greater than T up, because again, it took longer for the ball to reach the ground because it has higher dy compared to this one moving upward, which only has a shorter dy. And our answer now is 105 meters. So that will be all for today. Thank you for listening.